Hi, the lecture today is going to be about review of trigonometry. This is a topic we need now because we are going to talk about derivative of trigonometric functions. So I'm going to go ahead and do a quick review. Be sure to go and pick up a text on trigonometry and start studying it in detail. This is a topic that you are going to need now, and then in Calculus 2 and later on in differential equations. And then those of you going to engineering, you are going to need quite a bit of it when you study circuits in circuit analysis class. You're also going to need it in physics. So it's a topic that is known for its huge number of formulas, and essentially it takes about a year to study and understand all of them. And basically, best thing you can do is to study this alongside with the course as we go along. Okay, we are going to talk about angles. What are angles made of? So, angle is made out of two rays. So we have a ray here, another ray here. They intersect at the point that's called the vertex, and the space between them, or the opening, is what's going to constitute the angle we are going to study. Well, we need to talk about angles in a much more specific way, and one way to specify an angle is to declare what is the initial side of it. So I might have an initial side, and then I will have a second one is going to be the terminal side. In that case, I'm going from initial side to the terminal side, and there is going to be a sense of movement. And in case we go in this direction, or the counter-clockwise direction, we are going to consider our angle to be positive. So counter-clockwise rotation is going to be considered as positive. Opposite of that, of course, if I had declared this one to be the initial side and this other angle to be the terminal side, then I'll be traveling in the opposite direction. In that case, this is a clockwise angle, and such angles are considered to be negative. So here we have negative angles, and here we have positive angles. That's just by definition. Next, with the same initial and terminal side, there are many angles associated. So there are infinitely many angles associated with the same initial and terminal sides. What does this mean? Well, if you go ahead and draw the same angle that we had over here, this being the initial and this being the terminal side, I could start from this point and travel in that direction. I could also start from the same point, travel, go around, come back, make one whole round, and then travel through the angle again. And of course, I could do this 3 times and 4 times, as many times as I want. That's going to be a winding number, so we are going to have a winding number indicating how many times we have gone around the origin or around the vertex. So if we are going in this direction, a winding number is going to be positive. And similarly, if you have initial and terminal sides in this fashion, you could just come once, or you could perhaps circle quite a few times. So this orange colored angle and this purple colored angle, they all share the same initial and terminal sides, and we have to be aware of it. Okay, to make this situation a little bit more clear, what we are going to do is to put angles in standard position. So next we are going to talk about angles in standard position. By that we mean that we are going to put our angles on the x-axis on the positive side. So we consider this to be the x-axis. Say this is the origin, and when I want to talk about an angle, I put the initial side here. So this is going to be my initial side, and a terminal side wherever it might happen to be. So if, for example, here is the terminal side, and perhaps my angle is just that. Well, perhaps the terminal side is here, or in this location, or in this location, as the case might be. Remember, if you have an initial and a terminal side, that by itself does not clarify what the angle itself is. So it could have been this is the initial, and then I traveled in counterclockwise fashion, and then I ended up at the terminal side. So you need the initial side, you need the terminal side, you need the direction of movement, and you need the winding number to actually specify an angle. When we draw a picture like this, we might go ahead and just draw the full XY coordinate system, and it helps to draw a circle centered at the origin. We are still imagining that the initial side of the angle is on the positive side of the x-axis, and the terminal side might be in any of these sections of the page. So I might have an angle that is perhaps ending up here. In that case, I'm going to say I'm in quadrant 1. Terminal side might be here, in which case I say I'm in quadrant 2. Terminal side could be here. I would say I'm in quadrant 3, and I could be here, and I say I'm in quadrant 4. It is traditional to talk about angles by using some Greek letters. So you have most common letter here is going to be theta. So our angles are typically termed theta. But here are the other letters of alphabet that get to be used. So you might as well be familiar with the alpha and beta and gamma, typical letters used. Now, when we are going to talk about the angles, circles come in naturally, so we might as well go ahead and do a quick review of that topic. We need to know what's the circumference of a circle. So if you have a circle comes in with a radius. By circumference we mean if you put a rope around the circle, how long would the rope be? Well, the length of this, sometimes shown by the letter C for circumference, is equal to, do you remember what that formula is? 2 pi r. Whose pi is that very famous number, 3.14159265, etc. Over the ages, people have spent quite a bit of time figuring out pi to billions of digits. So a few of them would be enough for us. Next topic we want to talk about is measuring angles. Of course, the most convenient unit that we have for measuring an angle is just how many circles are being occupied by the angle. So one circle or one round or one rotation or one cycle refers to an angle that just goes around the origin one whole round. Well, that's a big angle. Customarily it's divided to smaller portions for more accurate measurements. Most traditional way of measuring angles using degrees. One circle gets to be divided to 360 degrees. Most of the trigonometric courses work with degrees, but in engineering, due to requirements of calculus, we like to use some other unit. And that unit is the unit of radians. One circle is equal to 2 pi radians. Let me go ahead and explain what this means. So let's go and draw a circle. And here is the radius of it. Suppose this is R, the radius. I take a rope the size of this radius and just lay it on the circumference of the circle. So here is, I put it once perhaps. So this blue rope is equal to this blue rope in terms of its length. Then I put one more round. Then I put one more. Then again, this is 4. Here I put 5. Here's 6. And almost a quarter is left over. You notice that a circle could be sliced to almost 6 1/4 of these slices. Each of them is referred to as 1 radian. That is, if you connect this thing to origin, this angle that you are going to form here, this is going to be 1 radian. So if you come up all the way up to here, this is going to be 2 radians. If you come here, it's 3 radians. 3 radians almost straight angle, 180 degrees. By the time you come here, you have made 4 radians. This up to here is 5 radians. Come here, 6 radians. You make a full circle, you have almost 6 1/4 radians. So exactly how many radians is a whole circle? Well, 2 times pi radians. That's what a circle is. 2 times pi makes 6.28. One circle is equal to 2 pi radians. There's another unit that is available for measurement, and that's grad. One circle is divided to 400 little sections, and each little piece is called a grad. So a circle becomes 400 grads. On your calculators, you see that there is a button or some option here that typically flips between D or G. D, R, and G refer to here D, and here's R, and here's G. You switch between these units when you are doing your calculations. Remember, in calculus, what we need to work with, even though this is rather unfamiliar notation, we need to work with radians, otherwise our differentiation formulas have to be changed. Okay, if you want to convert from one unit to another unit, this is the formula you use for quick conversion. Next item that we might want to mention a few words about it is some basic facts from geometry. If you have any arbitrary triangle, what is the sum of the angles in that triangle? Sum of angles of a triangle, of any triangle, is equal to what? Well, this is one of the basic facts you need. Here's a quick reminder of where the whole thing comes from. Draw a line parallel to one of the sides. One basic fact from geometry is that these two so-called alternate interior angles are the same, and these two are the same, and the size of the angle that you see on here, this whole thing is one straight angle. One straight angle is half of a circle, or 180 degrees. Sum of all the angles of any triangle is 180 degrees, or is equal to pi radians, or 200 grads. So sum of these three angles is this big angle, straight angle here. A triangle that you see very often is a so-called right triangle, when one of these angles is 90 degrees. So 90 degrees is sometimes referred to as a right angle. If that's the right angle, then the other two angles that you have, this one, let's call it alpha, and this one, call it beta. Alpha plus beta is going to be the other 90 degrees of the total sum of 180 degrees. Alpha plus beta becomes 90 degrees. 90 degrees in notation of radians, it's going to be pi half radians. Any two angles that have this property that their sum is 90 degrees are referred to as complementary angles. Okay, now let's go on and talk a little bit about the connection between radian measurement and a circle. Let me go ahead and take a circle here, and let's draw an angle inside it. So suppose this is some angle. The angle itself, we are going to call it, say, maybe theta. We go ahead and measure how big the circle is. Let's say that the circle has a radius r, and we also specify what the length of this arc is. Let's call it L. Big question is, what is the connection between these three quantities, L, R, and theta? Well, in fact, one way of measuring an angle is to, the definition of a radian measure of an angle is the ratio of the length of the arc in front of it divided by the radius of the circle. So this theta is in radians. Another way of writing the same thing is to say L is equal to R times theta. Same fact is being expressed here. So if, for example, a radius of a disk is 2 feet, so let's quickly do an example here. Suppose I have a circle, radius of it is 2 feet, and I am coloring a section of this circle that is just 3 feet long. Now the question I'm asking is, how big is the angle, sometimes referred to as the central angle here? So central angle in this case is going to be the ratio of the length of the arc, which is 3, divided by the radius of the circle, which is 1.5. This is 1.5 radians. Now if you want to know how big is it in terms of degrees, you have to use this formula that we talked about here. You want to convert from one to the other, you divide by this number and multiply by the other one. So that's a unit conversion. If you want to convert to degrees, you divide by the same, what's the size of the circle in the same unit, multiply by the size of the circle in the other unit, say degrees, and out comes whatever this number is. For example, in this case, I guess we get 540. When you want to talk about degrees, one notation, convenient notation, is to put a little circle that stands for degrees. Okay, one other formula that's going to be helpful for us later on is the area of a sector. So over there we had the formula for length of, this is the length of an arc. This is the arc. This is a central angle. So let me write it down. This is sometimes referred to as a central angle. And this was the important formula for us. Now, area of a sector. In the same picture again, we have a circle. We have slice of this circle referred to as a sector. So here's a sector. We want to find out how to calculate the area of it. Well, what do we need? Of course, we are going to need a radius of the circle, and we need to know how big this angle is. Let's call this angle theta. Area is theta over 2 times r squared. Let me justify this formula to you in two ways, so that perhaps the formula stays in your mind. If you had the whole circle, what is the area of the whole circle? Do you remember what the formula is? Well, the formula in that case is pi r squared. What does this pi refer to? Pi is really 1/2 of the central angle of the entire circle. If you go around the circle once, what is the angle? That angle we just mentioned, one circle is equal to 2 pi radians. So this is really the size of the angle, and then the angle gets divided by 2. The entire angle gets divided by 2. The 2's cancel, and so you see this formula in our high school text. Pi r squared is the area of the circle. But in general, if the angle was just any number, theta in radians, so theta in radians. If the angle is not mentioned, we always assume it's in radians. We have to just divide it by 2, multiply by square of the radius, and we are going to get our area. What's the reason behind this formula? Well, let me draw the circle one more round. Suppose I have the circle. And here's my slice. I go ahead, take my slice, and slice it even smaller slices, tiny slices like this. Now, what does each of them look like? Let me go ahead and color one of these slices. Let me enlarge that slice. The side of this is going to be r. The angle here is very small, so the shape of this slice is going to look like a very thin triangle. Now suppose the base of this triangle is just, let's call it the base B. How would you find the area of this? The area is approximately equal to B times R over 2. Is that right? Well, what's the formula you learn about in high school? You know, B times height divided by 2. That's a formula for a triangle. This is not quite a triangle because we have a little bit of a curvature here, and this height is approximately equal to same as this radius. So I can say the area of this little slice is going to be a base times height, which is same as the radius divided by 2. Now for each of these little slices, I can go ahead and do the same thing. It's going to be BR over 2, and then for the third one, again BR over 2, and the fourth one it's going to be another BR over 2, and so on. So I have a bunch of BR over 2's to add up. Okay, so I'll have BR over 2, another BR over 2. For each of these slices, I'll have a contribution like this. Well, how can I clean this up? I say go ahead and factor your R's, factor your 2's, and all of these B's, all the bases. If all the bases are added together, what am I going to get? Well, if I add up all the bases, I'm going to get length of the arc. So whatever it is, these are all these tiny bases. When I add them, this is just the length of the arc. Correct my writing here. Well, what is the length of the arc? We just had the formula here. Length of the arc is r times theta. So, excuse me, if this angle is a theta, then the arc in front of it is going to be r theta. So length of the arc is r theta, and half the height is r over 2. So this all boils down to theta over 2 r squared. The way it is written in that style, it makes more sense. This is, let's write it again, r theta r divided by 2, and the meaning of this is really base, this is height divided by 2. So this is kind of just like the formulas you had in high school. The only difference here is that what we consider to be base is a portion of a circle, is an arc. So this is our base. Height, well, any line that you draw from the vertex all the way to this base is going to be your height. It doesn't matter where you draw it, they are all perpendicular. So really you're just multiplying base by height and dividing by 2, and you get your formula. So this is the formula for the area of a sector. Okay, perhaps we are ready to start talking about trigonometric functions. So let's go ahead and get ready for that. Trigonometric functions, trig functions. Trig functions are ways of studying a triangle. So we go ahead and start drawing a triangle, a right triangle, to keep things simple. Now we have to choose one of these angles as our focus angle. Let's go ahead and be traditional and pick this, the one down here. This is going to be our angle. Let's call it theta. As soon as you choose an angle, then there is a terminology that comes with it. The side that is opposite of this angle is referred to as the opposite side. Side next to it is referred to as adjacent side. This one is referred to as the hypotenuse. Hypotenuse. Sometimes it's written without the H. So we are going to abbreviate these things because it's rather lengthy words. So we have our angle theta here. This is the opposite. This is the adjacent. And this is the hypotenuse. Okay. Now this is where all hell breaks loose, because we are going to associate 6 different functions of this angle to various ratios you could build out of these length of these sides. And that's why trigonometry becomes a confusing topic. We essentially have 6 different ways of talking about the same thing. And when you have different ways, you start establishing relationships between all those different terminologies, and that brings us a huge load of formulas. So let's get started. You remember that sine of an angle, is a ratio, or what? It's going to be ratio of the opposite to hypotenuse. And then we have cosine of an angle is going to be ratio of adjacent to hypotenuse. And then we have, of course, tangent of an angle is going to be ratio of its opposite divided by its adjacent. And the reciprocal of all of these things have names also. So so-called cosecant of theta is just a reciprocal of this. Cosecant of this angle is a ratio of its hypotenuse, of the hypotenuse by the opposite. Secant of theta is the ratio of the hypotenuse by the adjacent. And cotangent of theta is the ratio of adjacent by the opposite. So maybe I better go ahead and write the names for those of you who haven't even seen the names. So this is the sine, this is cosine, this is tangent, this is going to be this is secant, and this is cotangent. If this is all unfamiliar to you, do allocate 2-3 hours extra per week to go through trigonometry in parallel with the course. Otherwise, things might not work smoothly for you. Okay, what do we use these functions for? Well, from ancient times, almost like 2,500 years ago, people have developed tables of values for trig functions. Well, not all of them were in use 2,500 years ago, but some of them, or some modified form of it, was where people used it for measuring land, as well as for astronomy and astrology. Later on, it became an independent topic all by itself. Well, one way that you use these functions for is to specify properties of a right triangle. Sometimes the issue is referred to as solving a right triangle. Solving right triangle means that here's a right triangle. This right triangle has 3 sides and 3 angles. Information about some of these might be could be given to you, and the question might be to find the other pieces. So solving a right triangle simply means finding all the information about a given triangle from the available facts. So how do you solve a right triangle? Whatever information is given to you, you go ahead and find which one of these formulas are applicable to your case, so that you can go and find one piece of information you don't have about your triangle. For example, suppose I tell you that this hypotenuse is 3 and this angle here is, say, 40 degrees. How big are the other 2 sides? Well, let's go ahead, give some names to them. Suppose this is x and this is y. I ask myself, what relationship is going to connect these 3 quantities to each other? Well, what are these quantities? If this is an angle, this is going to be adjacent, and that's going to be hypotenuse. What connection do I have between these? Well, the connection I have is that cosine of 40 degrees is equal to x over 3. Cosine of this angle is adjacent over hypotenuse. So x becomes 3 times cosine of 40 degrees. No, either I have access to a table where people have developed cosine of 40 degrees for me, or I have a calculator, I use it and find out what the x happens to be. So solving a right triangle means taking these formulas and deciding which one of them is useful in a given situation and rearranging them until you get the quantity that you want. Just like we did here, we rearranged until we found the quantity x. If I wanted the quantity y, what formula would be useful in that case? Well, I go ahead and say between these three quantities, y, 3, and 40, what's the connection I can establish? Well, the connection is sine of 40 degrees is related to these two other numbers, opposite divided by hypotenuse. So you can say y is equal to 3 times sine of 40 degrees. And that is going to specify the length of side y for you. Okay, next topic we need to look at is the trig functions for arbitrary angles. What do you mean arbitrary angles? Well, all the discussion that we had here was geared to a right triangle. By necessity, these angles that you have here are less than 90 degrees. What if I had an angle that was larger than 90 degrees or was a negative angle? How would I handle the question in that case? So arbitrary angle means an angle could be in the second quadrant or third or fourth, or negative angle. What would we do in those cases? Well, there's a convenient way of moving into the general case. First, we start by a coordinate system. The angle that we are interested in, we put it in a standard position. So initial side goes on the positive side of x-axis, and terminal side could be wherever it wants to be. Suppose this is a terminal side, and say this is an angle. Or perhaps I have traveled in a negative direction, or perhaps I've gone around the circle around the origin several times and stopped here. At any of these cases, all I need is the location of the terminal side. Next, I go ahead and find some point on this terminal side, doesn't matter, any point, and I ask myself, what are the coordinates of this point? I need to figure that out. So coordinate of that, I'm going to have an x and a y for the coordinates. Also, I'm going to find out how far I am from the origin itself. That is, I find this distance r or radius or whatever it is. So in the familiar case, it would have been if I was in the first quadrant. Let's draw a picture for that too. Suppose my angle was just an ordinary angle in the first quadrant, and here's my angle. I have picked some point here, and I'm going to call this point coordinates x and y, and this is going to be r. Now let's remember what is x and what is y. X is this. So here's the x. Who's the y? Y is this one. And who's our angle? The angle in both cases, here's angle, say theta. Well, how did you define sine of theta? You had it defined as opposite over hypotenuse. Well, just use the coordinates now. Opposite y over hypotenuse is r. How about cosine of theta? Cosine was adjacent over hypotenuse. So now call it x over r. Who was tangent of theta? Tangent of theta was opposite divided by adjacent. So this is going to be y over x. You notice what's happening. What's happening is that we are just, instead of calling it opposite you're changing that for the y coordinate. So this is playing the role of opposite, assuming that your angle is in the standard position here. This one is going to play the role of adjacent, and this one is going to play the role of the hypotenuse. If your angle was in the first quadrant, you didn't need to go do all this renaming. But if your angle is in some other quadrant, you no longer have the notion of opposite. What do you like to consider as the opposite here? Who is the adjacent? And questions like that, the signs of them is going to be a difficult issue. So instead of dealing with the issue with these words, sign with the opposite and adjacent and such, we just refer to coordinates, and that's a much cleaner description. So let's go ahead and write the other formulas as well. You remember cosecant was a ratio of the hypotenuse to the opposite, so it's just a reciprocal of this. And secant is a ratio of hypotenuse to the adjacent, and cotangent was a ratio of adjacent to the opposite, and so on. So main difficulty is overcoming 6 similar sounding functions, their definitions, and so on. So that is something that you need to struggle with. Okay, once you digest the definition of the functions themselves, there are a bunch of trig identities that we need. So next issue is trig identities. Well, there are more trig identities than there are boxes of cereals in a standard supermarket, so you need to kind of understand them and know when to apply them and what do they mean and where they come from and so on. Otherwise, trying to memorize them is a rather hopeless task. You have to memorize them, but you need to also understand them. Okay, trig identities come in several flavors. One of them, most basic, are so-called Pythagorean identities. These are all related to Pythagorean Theorem, the most famous theorem in geometry, sometimes referred to as bride of all theorems. Okay, let's remember we used to call this x and this one y. We might as well use the same notation. It will be a little bit easier to digest it. So what was the Pythagorean theorem? It said that x squared plus y squared is equal to what? Is equal to r squared. Well, that very famous formula translates into quite a few identities for us. In fact, large number of identities in this topic all come back to this. They're all children of this. Let's see, how do we take this thing and convert it to a trig identity? Remember, all the trig identities or functions are based on ratios, not on the quantities themselves, but the ratios of two lengths. So if I want to make a ratio, I have to divide by something, and I better divide by a square of that something. So what do you divide by? Well, whatever you decide is going to give you one identity. Suppose I say divide by r squared. I can divide by anything I like. Suppose I divide by r squared. So x squared over r squared plus y squared over r squared is equal to r squared over r squared. But what is this? R squared over r squared, that's just 1. What is this one? X over r squared. Who was x over r? X over r. Let's focus on this angle. Let's call this one our focus angle. Let's call this theta. Who is x over r? You remember x over r, ratio adjacent to the hypotenuse. That's just cosine. So I write this is cosine of theta. Since I'm squaring, I'll be squaring. Who's y over r? Y over r, opposite over hypotenuse. That is going to be your sine, which is being squared here. So here's our famous first formula: sine squared plus cosine squared is equal to 1. Now, once you have one of these identities, you can always make quite a few other ones out of it. They are like children identities. We don't need to memorize every single one of them, but it's good to see them. Cosine square, same as 1 minus sine square. Another way, you can write sine square is equal to 1 minus cosine square, and so on. Okay, let's go back to this Pythagorean theorem. Here I divided by r squared. What else can I do? Well, I could divide by x squared or y squared. Either case, I'll get something. Let's go ahead and try it. I take this, divide everything inside by x squared. Now, you pause this thing for a moment and convert it to trig identities and come back and tell me what you got, okay? So you pause and you come back. I draw my triangle here again. Remember, this was x, this was y, this was r, this was theta. X over x, that's just 1. Who's y over x? Remember, opposite over adjacent, that is tangent. What is r over x? Hypotenuse over adjacent, that is secant. So that's our formula number 2. Again, you can make some related identities quickly, like you can say tangent square of theta is secant square of theta minus 1. Challenge is, whenever you see this, you have to remember that, and that's a big challenge, and only comes with extended practice. Nobody can actually, most people I know can't just memorize these things. Okay, round 3. I can take this and divide it by y squared this time. So my formula is going to look like x squared over y squared, excuse me, plus y squared is equal to r squared over y squared. Who are these? X over y. Let me, x over y is adjacent over opposite. That is cotangent. Y over y is just 1. R over y. Who's that? Hypotenuse over the opposite. That is cosecant. So it's third version of Pythagorean identity, and that gives you what? Gives you cotangent squared is cosecant square of theta minus 1. It's good to see all of these things in another context as well. This identity really says that if you have a right triangle and the hypotenuse of it is 1 and this is theta, then this side is cosine and this side is sine. Just go ahead and convince yourself this designation is correct. Ratio of adjacent to the hypotenuse supposed to be cosine, is it? Well, yes, it is. Ratio of opposite to hypotenuse supposed to be sine, is it? Well, yes, it is. Now, let me see if how well you understood that. Suppose this is the angle theta. Go ahead, use these 3 values: 1, tangent of theta, and secant of theta. Put it on these 3 sides and tell me who's going to be 1, who's going to be tangent, and who's going to be secant of all the 3. Well, if this is 1, then the opposite has to be tangent, and this will be secant. Round 3. Go ahead and designate these sides. Here's the angle theta. Who is 1? Who is cotangent? Who is cosecant? Okay. if this is 1, ratio of adjacent to the opposite has to be cotangent. Ratio of hypotenuse to the opposite is going to be cosecant. Okay, if all of this became too much already, just make sure you remember this one and that picture. We are going to need it pretty soon. Other bunch of identities are referred to as ratio identities, or sometimes reciprocal identities. Well, most famous among these is what is the relationship between tangent and sine and cosine. Let me go all the way back here. Perhaps it will be easier for you to see. What's the connection between tangent and sine and cosine? Obviously, if I divide sine by cosine, r's cancel and I get y over x. And that's going to be tangent of theta is equal to sine theta over cosine theta. What else? Cotangent of theta is a ratio of cosine over sine. Just take the ratio, you will see. Cosecant is a reciprocal of that. Secant is a reciprocal of this. Cotangent is a reciprocal of tangent. So we already got one load of formulas. Let's go ahead and write sine of theta over cosine of theta is going to give us tangent. Turn everything upside down. We'll have cosine over sine. What else we get? We got that secant is 1 over cosine. Cosecant is 1 over sine. Cotangent is 1 over tangent. Or you could write it around. You could write cosine is 1 over secant, and so on. Next, a bunch of important identities called negative angle identities. At issue is that what if our angle was negative? Can we conveniently transfer it back to a positive angle that we are more familiar with? Let's go ahead and draw a coordinate system to respond to this situation. Here's my coordinate system. I have, say, an angle here, angle theta, positive angle, and I draw the negative angle. Easiest way to draw that negative angle is just flip it across the x-axis and go in the other direction. So that's going to be negative theta. That is positive. That is negative. Okay, I want to talk about various trig identities. I might as well pick a point here and complete my triangle. Just go straight down all the way. Suppose this point has coordinate x, y, and this distance is r. What is going to be the coordinate down here? So if you flip over, it's the y that becomes negative. Okay, now let's go ahead and suppose I want to write sine of minus theta. Here's my angle. Sine is a ratio of the y coordinate over the distance from the origin. Y coordinate is minus y, and this distance is same as distance up there. It's just, now who was y over r? Let's write it like this. Y over r, this is y divided by r, that's sine of theta. So that's just minus sine of theta. To write it clearly, sine of minus theta is minus sine of theta. How about cosine of minus theta? The cosine of minus theta is a ratio of its x divided by r. But x here and x here are the same. So that's the same as cosine of theta. How about tangent? Tangent of minus theta, tangent of this angle, is its y coordinate, which happens to be minus y, over its x coordinate, which is x. This is minus y over x. Well, y over x was tangent of theta, so this is really minus tangent of theta. To write it nicely, tangent of minus theta is equal to minus tangent of theta. So 3 identities to remember. Sine of negative of an angle is a negative of sine of that angle. Tangent of negative one angle is negative of tangent of that angle. And let me rewrite this observation separately also. Cosine of minus theta turned out to be same as cosine of theta. So you can also go ahead and write the reciprocals of all of these things. I quickly go ahead and write. Reciprocal of sine, you remember, was cosecant. So cosecant, just like this one, is going to have a surviving negative signs in it. Let me go write that also. Cosecant, actually, cosecant of minus theta is going to be minus cosecant of theta. Secant of minus theta, secant is a reciprocal of cosine. It's going to have same property. It's going to be equal to secant of theta. Cotangent, well, cotangent is a reciprocal of tangent. Is going to have the same property, minus cotangent of theta. Or if you wish, you can always draw the same picture I drew here and compare the function of this negative angle with the function of that positive angle and see how do they relate to each other. Some places the minus goes away, some places it stays. Where is it that the negative disappears? For cosine and secant, negative disappears. All the other ones, negative stays. For that reason, this type of functions were called even in college algebra, if you remember. The rest of them, where negative survives, they're called odd functions. Okay, this all brings us to climax of all of these things. Very important identity we need it for our differentiation in the next lecture, and that is a sum of angle identities. At issue here is if I have an angle, let's call one of them alpha, and I have another angle, say beta, and I want to find the sine of the sum of these two. What is that going to be? If you remember, that is sine of first, cosine of second, plus cosine of first, sine of second. This is one of those identities that I mean to talk about, and let me go ahead and show you where it comes from. Those of you who intend to go far with these topics, you need to know what's the origin of it. There are many proofs for these things, basic formulas, and here's one. All of them use a unit circle in some fashion. Unit circle simply means a circle of radius 1. Let me go ahead and make it kind of a big circle because my picture well, it didn't turn out to be all that good of a circle, but it's okay. So here's my center. Here is the x-axis. I go ahead and draw an angle, call it alpha. Let's choose this color. Suppose this is my angle alpha. And then the angle beta. I add on top of that, so this is beta. So alpha plus beta is this whole thing. Okay, let's see if you can draw this thing carefully. Start from here, drop a perpendicular to this blue line, and from there drop another perpendicular to this. We are taking this to be a unit circle, so a radius here, take it 1 for simplicity. R is equal to 1. First question, how big is this, forgetting what color that is, bright purple line from here to here? This is angle beta, hypotenuse is 1. This, what is that? Let me help you out. Hypotenuse 1, angle is beta. What's the opposite? The opposite is going to be sine of beta. Is that right? This is sine of beta. How about this one? Well, that is this adjacent side. What's that? That's going to be cosine of beta. Next, how big is that one? Showing the same color. This orange color here, orange yellow color. Maybe I'm color blind. Let's see, whatever this color is, how long is that? Let me draw it on the side. I have a circle that looks like this. This blue section from here to here, that was cosine of beta. This angle is alpha. Question is, how big is this? You remember that solving a right triangle, ratio of that to that would have been sine of alpha. So sine of alpha times cosine of beta becomes the sine of alpha times cosine of beta. That is the size of that. Go ahead and make sure you convince yourself this is sine of alpha cosine beta. Okay, for the more interesting part, now we are going to do something rather unexpected. We are going to go straight up and drop another perpendicular here. Next question, how big is this one? You need some background in geometry to see this. This angle, I claim, is same as alpha. Why so? Because alpha and this angle are complementary. Alpha and this alpha and this angle make 90 degrees. That angle plus this also make 90 degrees, because 90 plus this 90 makes 180 degrees for this straight line. So this angle here is alpha. Remember, this was sine beta. This angle is alpha. Let me draw it on the side. I have a picture looking like this. This one was sine beta. This angle is alpha. What is the length of this green line? Okay, you go ahead and figure that out for me and come back. The length of this green line, you solve this right triangle and find out that has to be sine of beta times cosine of alpha. Sine of beta times cosine of the adjacent angle. So this is sine of beta cosine of alpha. Okay, what does all of this do for us? Consider the line straight from here to here. How long is that line? Well, half of it is same as this one, sine alpha cosine beta. The other half of it is sine beta cosine alpha. So this one is this plus that. Let me write. Sine of alpha cosine beta plus that one, sine beta cosine alpha. What do we do with that? If I was to ask you what is sine of alpha plus beta, you would say the opposite divided by a hypotenuse. Well, hypotenuse is just 1. So sine of alpha plus beta is equal to sine of alpha cosine beta plus sine beta cosine alpha. I wrote it a little bit different than what I wrote up there. Okay, this is one of the proofs of this. You might have seen another proof, probably a different one, in your trig class, perhaps the one using the law of cosines at the end of your trig semester. Let me just write for good measure another formula. Cosine of alpha plus beta. Let me see if you can construct a proof for it, just like the one I did here. If you come up with one, let me know what you have done. This is cosine of alpha cosine of beta minus sine of alpha sine of beta. And then there is another one for tangent. I just write it. It's obtained by taking the ratio of these two. Tangent of alpha plus beta, ratio of that one to this. We go ahead and divide everybody by cosine. Cosine of alpha cosine beta, and we end up with the following formula. Tangent of alpha plus tangent of beta over 1 minus tangent of alpha tangent of beta. Okay, I guess I stop here, and the next lecture tomorrow is going to make use of all of these identities. Especially we are going to need this one. For tomorrow, plus we need some inequalities also. So that's going to be another bunch of formulas to consider before we get going with the formulas for the derivative of sine and cosine. Okay, you go ahead and take a look at your trig text. You can just go and get any one of them out of the library. Typically faculty in math department have trig books to give you for free if you need one, and just spend some time learning this. We went through this thing rather quickly. In 1.5 hours we did what typically takes 3 or 4 weeks to do in a pre-calculus class. So you give yourself a little bit more time to digest all this material. Good luck and God bless.